Okay, right. Cool. Now I want to show you briefly how do you use the table that is found in clause 9.2 of the standard. Clause 9.2 has a table that actually determines or what should be on the bit stream, or how should your bit stream look like depending on the number of non-zero coefficients that you have in your block. Does that make sense? Cool. So now this table, it's important to understand how this table works. So in that table, let's say I'm going to look at this table. I have to look at this table. It's not here. And then let's look at this table. We're going to look at this table, right? Right, we are going to look at the table. It's called table 9 5. 9 table 9.5, which is basically a table that we use to decode the coefficient token, to encode and decode the coefficient token. But in the standard is referred as table 9-5, coefficient mapping to total coefficient, open what do you call it? Open bracket coefficient token closed and trailing ones. So it's basically the table that is used to actually output the bit stream that represent the number of trailing ones, which we said it's the number of non-zero coefficients that have an absolute value that is equals to 1. Does that make sense? Those are trailing ones. The number of non-zero coefficients that have an absolute value that is equals to 1. So the table gives us the bit stream to represent that, but it couples that bit stream with the total number of non-zero coefficients that have a value which is not equals to an absolute value of 1. So basically here we are dealing with coefficients that are not equals to, that have a value that is not equals to 0. Because after you have done all the processes required by the standard during the encoding process, let's speak about the encoding process, because in H.264, we're actually speaking about two processes, the process that encodes and the process that decodes. So let's speak let me refer to the process that encodes. During the process of encoding, there's a set of steps and processes that you have to follow to actually encode your block. Does that make sense? Your block of a macro block. And I hope that we do understand by this time what a macro block is. A macro block, it's basically a block of pixels, a block of 16 by 16 pixel. Let me put the size of that a macro block. A macro block is a block of 16 by 16 pixel. So in H.264, every time a person mentions the name macro block, you must know that he is referring to a 16 by 16 pixel. And remember, a pixel, it's the smallest component of an image. Yeah? An image is found in videos, because in videos we've got moving pictures, which is basically moving images. So it's the smallest component. There's nothing smaller than a pixel. And a pixel is composed of 3 components: the red component, the blue component, and the green component, which are those in science. I remember in high school we referred to them as primary colors. It's the 3 components that make up a color of a pixel. But when it comes to H.264, we actually, when we speak of a red component, blue component, the green component, it's when we are actually speaking within the context or the let me say the vocabulary of a color space called RGB. But there are other formats of representing a color, which one of them is YCBCR, which is another way of referring to a color. So there we are referring to the Y component, which is the luminance component, how bright a pixel is, and then we have the CB, which is the blue component of that pixel, and the CR, which is the red component of that pixel. That's another color space. I don't want to speak about the science, but what I want to focus on it's the encoding. So when we speak about a block, a macro block, we're speaking about a block of pixel, and we know that a pixel is composed of those three components: the luminance component, the blue component, and the red the red chroma component. Does that make sense? So each of those components is encoded separately. So when we look at the table that is at clause number 9.0, that table actually would be used for each of those components, right? So we're going to look at one component. We basically follow the same process for each component. Does that make sense? So let's say in this instance, let's look at the luminance components, because with the luminance components, you can actually display something that makes sense. For example, we used to watch the black and white television. The black and white television only had one component, the luminance component. So I'm not going to go with the color spaces and how color spaces are. I want to look at how do you decode things from the bit stream, from the series of ones and zeros, and display them on your display. It doesn't matter where you display it. Do you display them on the color screen, or do you display them on the black and white screen? So 9.0 has a table here, and here we are going to assume that we are actually encoding the luminance part. The luminance part, which is composed of the blue component and the red component, the same process is just being followed. Does that make sense? But you must always understand that if you want a color, you are going to have those three components. If you are dealing with RGB is very good for display. What you see, what you are watching is in RGB format. But unfortunately for storage, it's not that convenient. So we use another color space when we want to do things for storage and for transmission, by the way, and for transmission, because the RGB, everything is needed. So that means the red component has to be there, the blue component has to be there, and the green component has to be there. While with the other color space, which is called YCBCR, we are able to remove the other things because they are not important. They cannot be perceived by our eye. The difference will not be perceived by our eyes. Does that make sense? So I don't want to go into the details of color spaces, but each pixel, it's important that you understand, each pixel is composed of three things. And here the color space that we are working with, because we are looking at storage, the color space that we are working with, it's the YCB CR color space. So here we are going to look at the luminance, the Y component. So that Y component is composed of coefficients, which will tell you how bright that image, that part of the pixel is. But an image is big. It could have something like 500 pixel across, and it could have 500 pixel vertically. So each pixel of that image, when we deal with an image, we actually break it into smaller images, and those images will be composed of 16 by 16 pixels. So that means we'll have those 16 by 16 by, we'll deal with a complete image that fits your screen as small images that are 16 by 16 pixels. Does that make sense? And those 16 by 16 pixels, block of pixels, we call or refer to them as a macro block. Every time we refer the name, That's the reason why I had to say all these things. Every time we say macro block, you must, in your head, in your mind, what has to go? It's a 16 pixel across and then a 16 pixel vertical. Every time when you say macro block, when a person comes and say macro block in H.264, you must know that, oh, that's a 16 pixels across, that's 16 pixels across. That 16 by 16, when we do the encoding and apply all the processes, we also subdivide it into smaller boxes. And each 16 by 16 a block of pixel, when we encode it, we go and subdivide it into 4 by 4 blocks of pixels. Does that make sense? So those blocks of pixels individually, we will refer to them in this video as blocks. We'll just say block for simplicity purposes. But a macro block has a name in H.264. It's a 16 by 16 a block of pixel. And then that 16 by 16 block of pixel is also subdivided into 4 by 4 block pixels. And that 4 by 4 block pixel is also go and be subdivided into 2 by 2 blocks. Does that make sense? So 2 by 2 blocks, I think it's the smallest division of pixel. So it will depend now on the encoder, the mode of encoding that is going to be used to encode each video. Sometimes the 2 by 2 block, you may have to look at things at 2 by 2 block. But most of you, and in this example, as we are working, we're going to look at the 4 by 4 blocks. So the macro block is composed of 16 4 by 4 blocks. Does that make sense? Each macro block, which is a 16 by 16 block, is composed of 16 4 by 4 blocks. Does that make sense? 16 times 16, you can count. Now, I think we should get something like, let me press my calculator here. How many blocks of pixels are these? Because we don't want to mislead people, good people. What we want to say the exact things to. Oh, Jesus. Where's my calculator? Where's my calculator? I want to see how many blocks of pixels do we have in a 16 by 16 block of pixel. Then we will, where's my calculator? It should be on Samsung. And then, it's not here. Calculator. 16 times 16. So that's 256 pixels altogether. That's 256 pixels. So these 256 pixels, we also divide it into 4 by 4 blocks. 4 by 4 blocks. 4 by 4 blocks is equals to 16, right? So that means each block in a micro block, each block, remember we said a block, it's a 4 by 4 block of pixels, which means it's 4 by 4 block of pixels, it's 16 pixels altogether. Each 4 by 4 block is composed of 16 pixels, and we have 16 of those 4 by 4 blocks in a micro block. Does that make sense? So here, the smallest component that we are going to deal with, it's a 4 by 4. It's a 4 by 4 block, which is composed of 16 blocks. So all the transformation from the DCT discrete cosine transform what is this? DCT, discrete cosine transform. There's a mathematical function called discrete cosine transform that we apply to the values of the each of the 3 components of each pixel, which those components, we said there are 3. There's the red, there's the blue, there's the red, there's the green. But we said this is these components, they are referred this way when we are dealing with the RGB color space. But when we are dealing with the YCP RCR color space, actually images, when they are captured in their natural form, they are captured in the RGB color space. And then when we want to do encoding, because when we do encoding, it's when we don't only transform the physical values that we capture from the camera, from the physical world, into the digital, but it also has to do with trying to reduce the amount of space that would be required to represent whatever we have captured from the physical world, because we've got a limited storage, né? And we've got a limited network transmission. So when it is captured in RGB color space. Bam! The camera takes an image. So the image will be taken as RGB. And after we have taken that RGB, now we want to process it. That means we want to convert it into a series of ones and zeros so that we can store it in a computer, because that's the only way to store things in your computer. The way our physical world is structured is totally different with how computers actually represent data. So we capture this thing from their physical format, and then we convert them into digital format. And when we convert them into digital format, we actually convert them into a totally different format. Does that make sense? To save space. So an image will be captured in RGB color space by the camera, but then the encoder, there's a software that is inside that a phone which will be capturing, if we are using a phone, if we would be capturing that with a phone, there's a software inside that phone that is going to take whatever is captured physically and convert it into digital. So that software has the responsibility of taking that image, convert it into another format that is suitable for storage and network transmission. And that format is called YCBR. It's called Y for luminance, and then CB for the chroma component, called the blue component, and then CR. Why is it not appearing here? All right, I will write it here. So the image is going to be captured from its physical component, physical color space, which is RGB, right? And then it's gonna be converted to YCBCCR, right? It's gonna be captured in this format, and then the software inside whatever device that will be capturing that image, it's gonna be converted into YCBR. The YCBR, the Y in this YCBR is for luminance, which is basically how bright that pixel is. And then we have the CB, the chrominance, which is basically chrominance blue component. And then we have the chrominance red component. The green component is actually, when we use this YCBR color component, is being chrominance, right? The red component. So this one is a blue component, chrominance. So the YCBR is only concerned with the blue component and the red component. The green component can be created from the blue and the red component. I didn't want to go into how color spaces work and all of that. I just wanted to focus on how data is encoded. Ne? The image data is encoded, guys. But you know, sometimes when you know too much, maybe when you've got a lot of things, you just end up saying things that you didn't want to say. But here's the basic. Here's what I want us to understand, is that there is a color space that is suitable for display, for what you see. There's a color space that is suitable for display, but it's not so good when we want to store things and when we want to transmit things from the device that captures and the device that is going to receive. Ne? There is just a a very, there's just these two color spaces. They are just suitable or good depending on what you are using them. The RGB is good for display. Let me make it simple like that. The RGB is good for display, and then the YCPR is good for storage because you save a lot of space when you do when you use the YCPR, and then it's also good for transmission on the network because the resources to transmit things from one device to the other one are very expensive. So the YCPR is very good. The RGB is good when you want to display. Does that make sense? So when we capture things in this format, an image, and then because we want to store this thing in our phone, then there's a software inside our phone that is going to convert that into this YCPR. After it has converted this into YCPR, and then it's going to deal with these three components separately. And that's the process that we're doing. We're looking at the process that is used to deal with these three components of the YCPR color space. The Y, which stands for the luminance, how bright that pixel is, right? So we look at the luminance, we look at the chrominance, and we look at the red chrominance. These processes, they are the same for these three components of each pixel. They are the same. Does that make sense? They are the same. You apply exactly the same component. So we'll look at them as the same. So when we say we have a 16 pixel or a 4x4 block, that means we could be looking at the luminance component of the pixel, or the red or the blue, but the process is the same for all these components. So after an image has been captured, and then it's been captured in RGB, it's going to be converted to YCPR. After it has been YCPR, when we want to encode it, we are going to encode each component of that pixel separately, and this process that we are talking about, the H.264 process, the process that we found under the H.264, they are applied. They would be applied to each component of that pixels. Does that make sense? I hope this makes sense. Right. So now each pixel, and when we say pixel, we'll be referring to a component, luminance. Each luminant of the pixel, each luminant is going to have 16 pixels, and then each chrominance also is going to have those 16, and then each red chrominance is also going to have. But now, to make things simple, let's just say each pixel is going to have 16 coefficients. Now we're speaking about a block of a microblock. Remember, an image will be divided into what is called microblocks, right? And those microblocks will also be subdivided into blocks, right? And each microblock has a maximum of 16 blocks. It cannot have more than that, and it will not have less than that. If it has less than that, it's not a microblock. But if it does happen, maybe let's say an image, when it is divided into these 16 by 16, and there's a remainder and all of that, where there's a remainder, blocks will be added. That will be black, will be added as black and all of that. But at the end, an image, but when we do encoding, we actually work with 4x4. We work with 16 by 16 pixels, right? So this is a block that we are dealing. with. So now let's say after we have applied all the processes, we've converted, we've captured the image in its RGB format, and then we converted it into YCPR. Now we're dealing with these components. Let's say in the component that we're dealing with here of the block, let's say we have these values, and therefore we want to output a series of ones and zeros that is going to represent these zeros, right? Cool. So that's where the standard comes from. The clause 9.2 of the standard. Clause 9.2 of the standard gives us a table of how your bit stream should look like, depending on the values that you have on on your coefficient after you have applied all the other processes. I don't want to talk about the other processes. After you have applied all the processes that you need to apply from capturing that image in its RGB format, and then you converted it into its YCPR. Now you are applying the H.264 processes, processes such as DCT, discrete cosine transform, and then quantization and all of that. After you've applied to that processes, let's say you remain with these values. Now it's time to do what? To output a series of ones and zeros to represent what remains after you have applied all the processes on the values of all the values of your processes of encoding your image. Now this is what you remain with. Now it's time to do what? To output the corresponding series of ones and zeros. And what is that series of ones and zeros? The table that is found in clause number 9.2 of the standard gives you the bit stream that you should output, né? Right. So we have a table that is found on table 9.5. Table 9.5 is used to actually encode the coefficient token, a syntax element which is called a coefficient token. The coefficient token in it has two things. It encodes the trailing ones, right? And then it encodes the coefficient values, and the coefficient values which will be referred to as levels in H.264 terms. Does that make sense? We have a syntax element. We've explained what is a syntax element on previous videos, a syntax element. And then we have a syntax element that is called coefficient token. That coefficient token has two values in it. The first one is the trailing ones, and the second one, it's levels. And here on the table is referred as coefficient levels. Does that make sense? So what are trailing ones? Trailing ones, it's those non-zero coefficients here in this block. After you have applied all the processes, in that block, the coefficients that are going to remain, which are non-zero, the coefficients that are going to remain, which are non-zero, but have the absolute value which is equals to 1. Ne? We have non-zero coefficients that have an absolute value of which is equals to 1. Oh, Jesus Christ. After we've applied all the processes that we need to apply when we do the encoding on each block of a macro block, after we've applied all those values that will remain, all those non-zero values that will remain, which have an absolute value which is equals to 1. Those values are called trailing ones. Ne? Trailing ones. So those trailing ones, they are encoded separately. They are encoded separately. But you can only encode non-zero coefficients that have a value that is equals to an absolute value of 1 as trailing ones. You can only encode those values up to a number of 3. We must put this thing properly in a way that people understand it. We can only have non-zero coefficients with the value of an absolute value of 1, right? An absolute value, it's a value of 1. So in these non-zero coefficients, for example, here we have values that have an absolute value which is equals to 1. We have 1, 2, 3 of 1, 2, 3, 4 of those values. We have got non-zero absolute values which have a value of 1. In this coefficients, in this example, we have those values, we have 4 of those values, right? Now we are trying to encode a syntax element called coefficient token. And I'm saying this coefficient token in it has two values. It has, number 1, the trailing ones, what is called trailing ones, right? That's one of the values that you'll get from the value of coefficient token. The second value that you are going to have from the coefficient token, it's the coefficient token. That's what it is referred in the standard, coefficient token, right? Right. So what is trailing ones? Trailing ones, it's those values of the coefficients of this block, right? The coefficients of this block after all the processes have been applied. Now it's time to output the bit stream that is going to represent this block on the bit stream, right? On the bit stream, what are the series of ones and zeros to represent this block? Ne? Cool. Here we are looking at clause number 9.2 of the standard. So everything that we are saying here, you should be looking of the standard, the H264 standard, clause number 9.2. Ne? There's a table which is found at 9.5. There's a table there in clause number 9.2. There's a table which is called 9-5, right? That table is titled coefficient token mapping. Ne? Coefficient token mapping, and there are other things that are written there. You will see things like coefficient token and trailing ones, and that's what we are explaining. What are these trailing ones and what are these coefficient token? Does that make sense? Cool. But now we are looking at H264 standard. H264 standard, clause number 9.2. And there's a table there, 9.5. There's a table 9.5. There's a table 9.5, right? That's the table. And that table is titled, and it's titled to tell you what that table is. And you'll find that there are a lot of zeros and ones there. And we're trying to explain what those zeros and ones represent, right? So that table gives you two most important things, right? It's the number of non-zero coefficients that are greater than 1, an absolute value of 1. And then it's the number of coefficients that are equals to an absolute value of 1. And those coefficients that are that have a value that is equal to an absolute value of 1, those coefficients are called trailing ones. And you can only encode the coefficients that are non-zero as trailing ones. You can only encode up to a maximum number of 3 non-zero coefficient values that have an absolute value that is equals to 1. It's important to understand this. It's very important. That is why I have to find everything that I can in order to explain it. Because if you don't understand this thing, I mean, I try my best to explain things to the best possible way that I can. Things that I know that I struggle to understand. So when we pass out the value that of the coefficient token syntax element, there we are looking for two things. There we are looking for the number of non-zero coefficients that are greater than 1. and then we are looking for the number of coefficients that have been encoded as trailing ones. And we say we can only encode up to a maximum number of 3 non-zero coefficients as the trailing ones. Those are coefficients that can be encoded as trailing ones. Those are non-zero coefficients that can be encoded as trailing ones, right? Non-zero coefficients that can be encoded as trailing ones, we can only encode those non-zero coefficients up to a maximum number of 3. If we have got more than that, then we must know that we can only encode three of them, and then the rest of them are going to be encoded as levels. Does that make sense? Levels are also non-zero coefficients, but it's those non-zero coefficients that have not been encoded as trailing ones. Trailing ones, what are those non-zero coefficients that can be encoded as trailing ones? Those